Hi, in our last video, we looked at first-order integrated rate laws. Now we're going to talk about the other integrated rate laws, namely zeroth and second order. I'm not going to talk about how these integrated rate laws are derived in this video. I've dropped a link to the video where I do that down below. I'm just going to talk about how we use them. So we're going to start off with the second-order integrated rate law. You can see that this second-order law looks somewhat different from the first-order integrated rate law. We still have the rate constant. We still have the time we want to know about. That part has not changed. But you will notice that there is no negative in front of the KT like there is in the first order integrated rate law. We still have our two concentrations, our concentration at time 0, the starting concentration, and the concentration at time t. But instead of having natural logs, we have the inverse, 1 over those concentrations. So let's just dive in and apply this rate law. Here we have a reaction that's a second order reaction. And we are asked how long it takes, which means that the time t will be our unknown for this problem. How long does it take for the concentration to drop from one molarity to the other? As usual, we start by making sure we have the right integrated rate law. The problem specifically calls out second order kinetics, so we get to use the equation I showed you earlier. So if t is our unknown, we need to plug in values for the rate constant and the two concentrations. We'll need to figure out which of our two concentrations is the A naught and which is the AT. Sometimes people have trouble figuring out which is which, but with integrated rate laws, we're always looking at reactants disappearing, which means their concentrations decrease over time. So the A naught will always be the larger of your two concentrations, and your AT will be the smaller of the two. So let's plug those values in, and then we're going to solve for t. This part over here simplifies to this value, and then we divide by the rate constant to get our time. Plug these numbers into your calculator, and you get 1.48 days. Here's a different sort of problem. It's still second order kinetics. We're still going to use the same rate law, but what we're looking for here is the rate constant. K is what we don't know. We know everything else. So let's find our value for AT and A naught. Again, AT is going to be the smaller of the two concentrations, and A naught is going to be the larger one. We also need to plug in our value for T, and we can spot that just by looking for something in the problem that has time units. Plugging those values into the equation, we then get to solve for K. Again, let's simplify this part with the inverses first, then divide by the time. And then we plug it into our calculator and we get a value for K of 0.00489 per molar per hour. All right, let's switch gears and talk about zeroth-order kinetics and the integrated rate law that goes along with them. Again, you'll see some things about this equation that are similar to the previous integrated rate laws and other things that are slightly different. We still have our KT, that's negative KT just like in the first order law. But now, instead of having natural logs or inverses of your concentrations, we just have your concentrations. So these sorts of problems work fairly similarly to what we've done before. Pick the correct integrated rate law, figure out what you don't know in that rate law, then identify the other variables in the problem. So this problem asks us what the rate constant for the decay is. We're looking for K. We know both of our concentrations. Again, AT is the smaller one and A naught is the larger one. And we're also given our time t, which here is 8 minutes. So let's plug those into the equation. Next, rearrange to solve for K. Now plug the numbers into the calculator and we end up with a rate constant of 0.0014 molar per minute. Now at this point in the first order integrated rate law video, we started talking about half-lives. So let's look at half-lives for zeroth and second order reactions. We're going to take the same approach to developing a half-life equation that we did for first order reactions. Basically, we're going to say that our concentration at time t is half of what it was at time 0. So let's just plug that into our zeroth order equation, and we get that half of A naught minus A naught equals negative K times the half-life. And if you do the math to solve for the half-life, what you end up with is our half-life is going to be the initial concentration divided by 2 times the rate constant. If you think about that, that means that a solution that's more concentrated at the beginning will have a longer half-life than a solution that's less concentrated at the beginning. Your half-life is dependent on the initial concentration, and so it is not constant. And you can definitely see that on this graph. As with the first order half-life graph, I made one that started at 0.2. And you can see that it hits 0.1 about here, somewhere around 125. And then let's go one more half-life. Where does it drop down to 0.05? You can see that's about 190, which is only 65 since the last half-life. Then the concentration halves again at, let's say, 225, a difference of 35. So the half-life keeps getting smaller as the concentration goes down. So what does half-life look like for second-order reactions? Once again, we're going to start with AT being 1/2 of our A0 and plug that into our second-order integrated rate law. Now, 1 over 1/2 of A0 is just, flip the fractions, 2 over A0. So we have 2 over A0 minus 1 over A0 equaling K times the half-life. And simplifying that, 1 over A0 equals K times the half-life. So our half-life is going to be 1 over the rate constant times the initial concentration. What does this mean? Well, again, our half-life is going to depend on what our initial concentration is. It is not constant. Now, I'm not going to show a graph for this one, but basically what will happen is that the half-life will increase as the concentration goes down. As the concentration goes down, the speed of reaction goes down. So both zeroth and second order half-lives are dependent on the initial concentration and therefore are not constant. As a result, we normally only talk about half-lives for first order reactions. Because we have a constant half-life, we can predict what that's going to be. So that's a very brief intro to using zeroth and second order rate laws. Like first order rate laws, they allow us to determine the relationship between time, concentrations, and rate constants. These are fairly straightforward equations, and a modest amount of practice will help you become comfortable with using them. I hope this was helpful, and I'll see you again soon.